If we look at a molecule of ethane in Chem 3D, we can see that the wedge dash depiction shown here has hydrogens coming towards us, hydrogens in the plane of the paper, and hydrogens going away. If we rotate this molecule slightly, so that we're looking down the carbon-carbon bond axis, we now see the Newman depiction. This is now a staggered conformation in which all of the hydrogens are at 60 degrees to each other, and therefore there is minimal interaction. We'll now define some positions here, in which the hydrogens on the back and the front, which are next to each other, are said to be gauche. The hydrogens that are on opposite sides of the molecule at 180 degrees are said to be anti, and we'll then start a discussion of rotation around the central carbon-carbon bond to discuss the actual energy of those different conformations. We can do this again by looking at the molecule from a Newman depiction perspective, and we now see that if we go to Calculations, Dihedral Driver, Single Angle Plot, one of the carbons will move relative to the other, and we'll see different conformations. So in this case, the back carbon has moved relative to the front carbon, and as we plot our way through 360 degrees, we see the least stable conformations are when all of the atoms are eclipsing, and the most stable conformations are when all of the atoms are actually not interacting. It is a staggered conformation, and if we press the cursor along the curve, we can see the intermediate looking different conformations where the atoms are starting to get close to each other, or indeed on the bottom of the curve, the atoms are getting further away from each other. Ethane is a fairly simple system in which all of the atoms attached to carbons are the same, and so the gauche and the anti and the eclipsed all tend to be equivalent along these reaction profiles. And we can see now from the textbook the actual rotation around that carbon-carbon bond with high energy maxima in which all the atoms are eclipsed, and then low energy minima in which they're actually staggered and either gauche or anti to each other. And the value for the rotation around this bond is 2.9 kilocalories per mole, which means that that's a significant amount of energy that's required to go through one of those rotations. And so as we move into more complicated molecules, we'll see similar graphs, and we'll recognize that molecules will tend to have a population distribution that is based upon these relative energies. Most of the molecules of ethane will look like the minima, and some of the molecules of ethane will look like the maxima, and some of them will look in between. When we extend our study of conformational dynamics to butane, we find that the graph will be more complicated. What we've done here is to move from ethane, we replace two of the hydrogens attached with two methyl groups, here and here. And so when we go through the rotation through 360 degrees, we'll find that the graph is somewhat different. So again, calculations, dihedral driver, single angle plot, rotate through 360, we now see that we have different maxima and different minima. The idea now is that the methyl groups will start to interact, and so we'll see different energy relationships dependent upon their relative proximity in space. Looking at the molecule from the side, we can see that the relationship between the two methyl groups is anti in this system, and if we then move the molecule around in order to form a Newman depiction, again we can see that the two methyl groups at the top and the bottom are pointing 180 degrees away from each other, and therefore anti. And we expect this to be the lowest energy system or the lowest energy conformation for this particular molecule. So what we'll do now is recreate the angle plot in the Newman depiction sense by doing the dihedral angle. We'll see rotation through 360. We find the same graph with the same maxima and minima, and now we can discuss the actual relationships between the methyl groups in terms of the Newman depictions. So at the bottom, we expect the lowest energy conformation to be that in which the two methyl groups are not interacting. As we move up this curve, we can start to see that the first minimum is based on an eclipsing interaction between a methyl group and a hydrogen. Once that moves into the gauche position, we see that the energy goes down. We now have a system in which the two methyl groups are gauche to each other, which is why this minimum is higher than the first minimum, the anti-conformation. And as we start to go up this part of the curve, we can see significant interaction between the methyl groups on the front and the back carbons, until eventually we get to the top, in which the two methyl groups are now completely eclipsed and interacting. If we move the molecule around, don't forget that the methyl groups are now on top of each other, and therefore that's the worst possible picture and worst possible system in terms of energy. As we head down this part of the graph, we can see the two methyl groups getting away from each other, back into the minimum, where they are gauche, and then back up to a local maximum, in which the methyl and the hydrogen are eclipsed, and then finally back down to the global minimum, in which the two methyl groups are as far away as possible from each other. The graph from the textbook shows the same idea, where on the left we start with the eclipsed conformation, in which the two methyl groups are on top of each other. This is the highest energy maximum. This then relaxes as we move down to the gauche possibility, where the two methyl groups are now away from each other slightly, and then we go back up to a local maximum, in which we now have eclipsing, but this is a lower energy than the original eclipsing because of the fact that we now have a methyl and a hydrogen interacting and not two methyl groups. The system then relaxes further to go to the anti-system, in which the two methyl groups are furthest away from each other, and then we go back through the rest of the 360 degrees to get back to where we started. So we see with this type of molecule that we can quite easily plot the changes in energy as we go from one conformation to another as they relate to the actual structures of the molecule. Here we see Newman depictions of selected conformations of butane around the C2-C3 bond. On the left we have the anti-conformation, which is also a subset of the staggered conformations, and this is the lowest energy minimum in which the two alkyl groups are furthest apart. As we begin to rotate around the central carbon-carbon bond, we now find that we get eclipsing interactions as the methyl groups and hydrogens start to interact, and this will be a local maximum. Go further with the rotation around the central bond, and we find that we get to the gauche possibility. This is also a staggered conformation, but because the two methyl groups are now close to each other, it is called gauche. To finish the set, we find that we have the eclipsed conformation, which is now where the two methyl groups are interacting, so this is a second eclipsed, which will be the highest energy possibility because now the two big groups are very close to each other. If we understand butane, we can apply this to all sorts of different molecules, such as those shown at the bottom, and this only works for acyclic molecules in terms of rotation around that carbon-carbon bond, but if we understand the pictures for butane, we can apply them to other systems.